Hello friends, this is Dr. Sonika Bhatia from the Department of Chemistry, Isabella Thoburn College, and today I will be talking about 2D NMR, particularly Cosy and heteronuclear Cosy experiments. So the correlation spectroscopy or Cosy experiments we have already done, and in Cosy it is a 2D NMR, that means it has got two frequency axes, one on the x-axis and one on the y-axis. The Cosy spectra, there can be two forms of the Cosy spectra, the stacked plot and the contour plot. If you look at the stacked plot, there are two frequency axes as I told you, F1 along the x-axis and F2 along the y-axis, and then there is another axis. You can see that the stacked plot looks, the intensity is coming in the form of mountains. It is going up. So these mountains are showing you the intensity of the signals. So actually if you see, a 2D NMR is basically a three-dimensional thing, because in the third dimension we have intensity. This particular plot is difficult to analyze, the stacked plot. So basically what is used in NMR is the contour plot. What is the contour plot? The same plot, but then cross sections of this plot has been taken. Like if you remember in class 10 you used to do contours and topo sheets. So similarly these contours are there, and the radii of these contours is telling us about the intensity of the signal. The bigger the spot, more intense is that particular signal. So this is a drawing of the 2DCH heteronuclear correlation spectroscopy. Why I say heteronuclear? As I told you that on both the frequency axes, the atoms are not the same. If you see here, we have proton NMR plotted, and here we have C13 NMR plotted. So both the atoms are not the same, so I refer it to as heteronuclear, and this is heteronuclear correlation spectroscopy. On the y-axis I have the proton NMR, and on the x-axis I have the C13 NMR, or on the F2 axis, this is known as the F2 axis, this is the C13 NMR, and this is the F1 axis where we have protons. And how do we find, if you see in the heteronuclear correlation, unlike Cosy, there is nothing on the diagonal. On the diagonal we get peaks only if it is a correlation spectroscopy, a homonuclear correlation spectroscopy. That means proton is PMR is plotted on this side and PMR is plotted on this side. Then we will get peaks on the diagonal. But here we do not get peaks on the diagonal. And what kind of correlation are we getting here? If you see, the correlation is that on the first peak of carbon at around 10 ppm is linked to one of the PMR. That means at 1 I am getting a triplet. So that triplet is attached, that these protons which are giving a triplet are attached to the carbon atom 1. Similarly, the carbon atom 2, I have got protons coming at 1.5 and they are giving a doublet. And if you see carbon atom 3, there are protons which are coming at around 1.7 and giving me a multiplet. And if you see the at 60 ppm, I have got a peak at 4. The protons are coming at 4. They are really downfield. And why are they really downfield? Because if you see, there is a chlorine attached. So the correlation which is coming out from this spectra is that carbon atom 1 is attached to proton 1. Carbon atom 2 is attached to proton 2, carbon atom 3 is attached to proton 3, and carbon atom 4 is attached to proton 4. This is the information which I have got from this Hetcor spectrum of 2-chlorobutane. We will see further how we analyze it. So what have we done? We have the information which we have got till now is that carbon atom 1 is linked to hydrogen atom 1, carbon 2 linked to hydrogen 2, carbon 3 linked to hydrogen 3 and carbon 4 linked to hydrogen 4. Now for the same molecule we have performed a Cosy. Now in Cosy or correlation spectroscopy, if you can see, on the F1 axis I have PMR plotted and on the F2 axis also I have PMR plotted. Since it is a homonuclear correlation, thus there would be peaks on the diagonal, but these peaks are not very important because the information which they give us is the same as 1D NMR. If you see, here is the peak, this is the triplet and it is getting linked here. So again the triplet, so it is the same. And if you see here, this is the second peak and this is linked to this particular proton. So this is the second peak, this is the third peak linked to the third peak here, and this is the fourth peak. So whatever information we are getting at the diagonal, the peaks at the diagonal are those which I can already get from the 1D NMR. So they are not important. As I had already told you, what is important is the off diagonal peaks, or also known as the cross peaks. So these cross peaks will tell me which two protons are linked. So let's see, from this first peak, the proton number 1, let me move horizontally. I come to this particular peak, and from this peak if I draw a vertical line, it touches 3. What does that mean? It means that proton 1 is linked to proton number 3. Both of them are coupled to each other. Now let me look at, so what do I do? In proton, in the column next to the column of proton 1, let me write 3, which shows that proton 1 is coupled to proton 3. Now this is the second peak, and if I move horizontally from the second peak, I come here, and this is the this is where this and from here if I draw a vertical line down, then where do I reach? If I draw a vertical line down, I reach to the fourth proton, the fourth signal in PMR. What does this show me? This shows that the second proton is linked to the fourth proton. So the second proton is linked to the fourth proton, or it is coupled to the fourth proton. Now let us look at the third signal. When I look at the third signal and move horizontally, I see that it is linked to two different protons. So from here, if I come to this peak and then start going down, I see that the third, so what do I see? That this particular proton is linked to the fourth proton. So the third proton is linked to the fourth proton. That is what this cross peak is telling me. And I can also see that the third proton, if I move this side, what do I see? If I move this side, then I see that the third proton is also linked to the first proton. So the third proton is linked to the fourth proton, and the third proton is also linked to the first proton, and that is what I have written here. Now let me look at the fourth signal. So if I look at the fourth signal, move horizontally, I see it is linked to two different things. The first cross peak is telling me that it is linked to the third proton, and the other cross peak is telling me that it is linked to the second proton. So these are the total number of correlations which I can get from this Cosy. And now let us make the correlation diagram here. So I start from C1, and C1 is linked to H1, so I have written H1 here, and H1 is then linked to H3, so I write H3 here. Now let me see, H3 is linked to which carbon atom? I will have to check in this column. H3 is linked to C3, so I write C3 here. Now H3 on one side is attached to H1, but see, it is to the other side, it is attached to H4. So I write H4 here. Let us see, H4, it is connected to which carbon? It is connected to C4. So I write C4 here. And H4, let's see how many neighbors does it have. It has two neighbors. It has H3 already drawn here, and it also has H2. So let me write H2 here. And then H2 is attached to which carbon atom? H2 is attached to second carbon atom. So I write second carbon atom. And that is the correlation. Let us check the structure. If you check the structure, carbon atom 1 is linked to hydrogen 1. Carbon from 1, then we have this carbon which is 3. From 3 I have another carbon which is 4, and from 4 is then attached to C2. So that is how we get the structure. Let's move on to other examples. Now I have taken a slightly difficult example. If you look at this particular example, let's see how many kinds of carbons are there. Let me count the kinds of carbon which are there in this molecule. If you see 1, 2, these two will be similar, so 2. These two will be similar, so 3, 4, 5, 6, 7, 8, 9, 10, 11. Total I have 11 sets of carbons. But if you look at the C13 spectra, you can see only 10 peaks. But it was then seen that this peak at delta 145.5 is composed of basically two unresolved lines. So on a higher frequency, it was checked and found out that this particular peak at 145.5 is composed of two unresolved lines. Now let us look at the hydrogen spectra. If you see, the hydrogen spectra is giving me 8 lines or 8 peaks. Let me check how many types of hydrogens do I have in this molecules. So 1, 2, 3, 4, 5, 6, 7, 8. I have 8 kinds of hydrogen. So all the hydrogens are giving separate signals here in PMR. Now let us draw the correlations. When I have to draw the correlation, what do? I see that hydrogen 1 is linked to which carbon atom? Hydrogen 1. Let us draw the line from here. This is the signal. I extend it upwards. I see it is linked to carbon 2. So I write carbon 2. Then hydrogen 2, let me draw a vertical line. You can use a scale and see. It moves and joins to carbon number 4. Similarly, signal of proton 3, and then let us extend it upwards. It connects to carbon atom 7. Signal at 4, signal for proton number 4. This particular proton, it then comes and connects to 8, and the integration value is showing us that proton number 4 is accounting for 2 hydrogens. Then proton 5, this signal for 5, if you see, it is joining and meeting signal 3 of carbon. Then signal 6 of proton is joining and meeting signal 1 of carbon. Signal 7 of proton is joining and meeting signal 5 of carbon, and signal 8 is going and meeting signal 6 of carbon. Again, signal 8 of proton is for 2 protons, right? And another interesting thing, if you see, you will notice that underneath the signal for 9 and 10, these two signals, under these two, there are no correlation lines. What does that show? This shows that carbon number 9 and carbon number 10 have no correlation at all. That means these are the peaks for unprotonated carbons. And of course, the low intensities of these carbons are also reflecting the same. If you remember, when we spoke about NO, that is NOE, when we spoke about NOE, heteronuclear NOE, we did talk about that if the number of protons which are directly attached to carbons are more, then the cross polarization transfer is more. Since there are no protons attached, so their intensity of 9 and 10 is less. So till now, what information we've got? Till now, the information we've got is which carbons are attached to which hydrogens. The same information which we did in the last spectra. I have taken the information and written it this way. Now, what do? We do a Cosy. Cosy will tell us which hydrogen is coupled to which other hydrogen. So let us see. On both the sides, we have taken a hydrogen spectra. So this diagonal line, since it is a homonuclear Cosy, so this diagonal line will have peaks, and this information we are able to derive straight away from 1D. So there it is not very important. Now let us see what happens. The first peak, if you draw a horizontal line, it is attached to second and it is attached to seventh. So it is attached to second proton and it is coupled with the 7th. So first I write second and 7th. Now let me look at the second peak. When I look at the second peak, it is attached to the first proton, or it is coupled to the first proton, and it is also coupled to the fifth proton. So if you see, the second hydrogen is coupled to the first proton and it is also coupled to the fifth proton. Let us start from here so that to avoid confusion. First carbon atom is linked to hydrogen number 6. This information we had got earlier. Now let us check hydrogen number 6. So hydrogen number 6, it is this particular peak. Now if you see this peak, there is no coupling for this peak here. On the horizontal line, there are no dots available. So I put a dash here. As I told you, for hydrogen number 1, we said that it is linked to 2 and it is linked to 7. Then for hydrogen number 5, let us see the scenario for hydrogen number 5. 1, 2, 3, 4, 5. This is 5. Hydrogen 5 is linked to the hydrogen at second position, the hydrogen number 2. Right? Now let's look, let's move further. When I move to hydrogen number 2, hydrogen number 2 is linked to 1 on one side and it is linked to 5 on the other side. Let's move to hydrogen number 7. 1, 2, 3, 4, 5, 6, 7. Hydrogen number 7 is linked to hydrogen number 1. Now, hydrogen number 8 is linked to 4 and there is a very little tiny dot here. This is negligible. Still I have written 3 and then written a W which states a very weak signal. Then hydrogen number 3. 1, 2, 3. Hydrogen number 3, if you see, hydrogen number 3 is linked to hydrogen number 4 and very weakly linked to 8. This we can neglect. Then hydrogen number 4, 1, 2, 3, 4. Hydrogen number 4 is linked to hydrogen number 3 and it is also linked to hydrogen number 8. And 9 and 10 are not linked to any hydrogen, that we had already seen. So thus there is no peak for 9 and 10 carbons because there are no hydrogens attached, so no peak in Cosy. Now let's try and fit these protons on the structure. If you look at the structure, in this structure, this particular carbon and to this carbon, this hydrogen which is attached, they are not coupled to anything. So they are isolated. Then there is one spin system here. If you see, these are 3 kinds of protons. First kind, second kind, third kind. So this is a system with 3 coupled protons. Then there is another system of 4 coupled protons. 1, 2, 3, 4. So I have 4 coupled protons. So we can see 3 systems here. How do I, it's easiest to start with a carbon whose hydrogen is coupled to only one other hydrogen because that will be the corner piece of the puzzle. Like whenever you are making a puzzle, you first of all, when you make a puzzle, you look for corner pieces. It becomes very easy to solve the puzzle then. Similarly here, when we start, we will look for those pieces wherein the carbon is attached to the hydrogen and the hydrogen is then coupled to any other hydrogen, just one hydrogen. Like in this case, if you see, this is the corner piece because it is this hydrogen is coupled to only one hydrogen. But this is a center piece because this hydrogen is coupled to 2 other hydrogen. This is a center piece. This is a corner piece. This is center, this is center, this is center. Let's start with carbon number 5. So I started with carbon number 5. To it I have attached hydrogen number 7 like here. From hydrogen number 7 I am getting hydrogen number 1. So I write hydrogen number 1. Hydrogen number 1, if you see, it is connected to which carbon? Let me check in the table. Hydrogen number 1 is linked to carbon number 2. Then hydrogen number 1 has hydrogen number 7 on one side, we've already written, and the other side it has hydrogen number 2. So I write hydrogen number 2 here. And hydrogen 2 is attached to which carbon? It is attached to C4. So we write C4. Then let's look at hydrogen 2. Hydrogen 2 has 1 on one side and 5 on the other side. So I write 5 here. And fifth of the hydrogen is attached to C3. So I write C3. That means indirectly I have got which carbons are linked to each other. So C5 is linked to C2, it is linked to C4 and it is linked to C3. So that is how I build the chain. And let me look at hydrogen 5. If you see, hydrogen 5 is only linked to one hydrogen and that is 2. That means this is the corner piece, right? Now let me look at this one. If you see here, I have hydrogen number 7. Sorry, I have carbon number 7 linked to hydrogen number 3, and this carbon number 7 is linked to hydrogen number 3, and hydrogen number 3 is linked to hydrogen number 4. This we are neglecting as it is very very weak. So I have written hydrogen number 4. Hydrogen number 4 is then linked to carbon number 8. So I write carbon number 8. Let me now look at hydrogen number 4. It has on one side hydrogen 3 and the other side hydrogen 8. So that is what I have written. And then hydrogen 8 is linked to carbon number 6. So this is the second unit which I have made. And if you see, the carbon here is linked to hydrogen 6. So this is the entire structure in front of us. Obviously, this piece here is somewhere here. This piece here will fit here. And this carbon hydrogen is C1. This carbon is C1 and this one is H6. Now let us look at this particular case. Here what will happen, these electrons will be in conjugation with the ring and thus at the ortho positions and the para positions I will have negative charge. That means the ortho and the para will be shielded. If ortho and the para are shielded, thus what will happen? You will see that they will appear upfield. So it is C7. This particular piece is C6. This is C8 and this is C6, right? Now if you look at these, here what will happen? The lone pair of electrons will travel from nitrogen and then electrons come here. Here I will have a negative charge and I will have a negative charge here. So these two will be shielded. Thus this is H2 and this is H7. So this is H2 and then this is H3. That means this one is C5, then C2, then C4 and then C3. And so we've been able to fit this piece as well and the structure is here. And as we had already discussed that accidentally signal 10 was for two carbon atoms and these the remaining three non-protonated carbons are, which ones are those? One is here, one is here and one is here. So signal 10 is for these two because it will be de-shielded as compared to this one. So signal 9 is for this one. Now let us do Hetcor of diethyl phthalate, right? So Hetcor of diethyl phthalate, if you see, this is the structure of diethyl phthalate. Hetcor shows contour plot signals of carbons which are directly attached to protons. That is J1 coupling. Hetcor only shows J1 coupling. So if you see, peaks at 167 and 132 show no contour. So what does that mean? That means that these particular carbons, both of them are quaternary. They have no hydrogen attached. Obviously, the one beyond 160 is for a carbonyl, for an ester, and here we can see the carbonyl. So the yellow dots are the ones which are appearing at 167, and the black dots are the ones which are appearing at 132. they are aromatic in nature, so 132. Then if you see, I have got two other dots, peak 131 and 129. They are both aromatic carbon signals, and 131 is this one. It is attached to, bonded to aromatic protons, and this says 129. So they are bonded to aromatic protons, and where are they? They are here. So if you see, these two will appear at one place and these two will appear together. So if you see, the bond here will be in conjugation with the C double bond O, and because of conjugation it will get a positive charge, and when it gets a positive charge, this particular carbon will appear at, if it is getting a positive charge, that means it is de-shielded. So this carbon will appear at 131 while this carbon will appear at 129. Now then there is another peak at 60 ppm. This peak at 60 ppm, if you see, it is linked to 60 ppm, it is linked to a quartet which is appearing at 4.3. So obviously we know by the study of 1D NMR that this quartet is because of the CH2, the green CH2. Then there is another one, peak at 10 ppm. So the peak at 10 ppm, if you see, is linked to the triplet, and this is the triplet. So this triplet is obviously because of this blue CH3 which is present here, and we have been able to correlate the entire spectrum. The two things more which I wanted to tell you, if you see in a Hetcor experiment, if you see that under one carbon atom there are two correlations or two lines. What does that mean? That means on that one carbon atom, two different protons are attached, and this is a case of distereotopic protons like I have made here. These two protons are distereotopic, and you must be remembering, when do the protons become distereotopic? They become tristereotopic when we have a chiral carbon attached. So whenever under one line in a Hetcor, the vertical line from the C13 spectra, you have two dots linking two hydrogens on the PMR, that means that those two hydrogens are distereotopic. And this is the pulse sequence of Hetcor, very similar to Cosy. After preparation, here we have a pulse sequence of 90x, and when a 90x pulse is applied, from the z axis, the protons come into the magnetization is transferred into the xy plane, and the FID is obtained. This is time t1, and then a polarization transfer from the hydrogen to C13 happens, and we apply another pulse, and then when we apply another pulse, a T2 relaxation happens and C13 is detected, and thus what happens here, then Fourier transform is done and C13 is detected. So on the F2 axis we have the C13 NMR, and on the F1 axis we have proton NMR. Now I would like to share something with you about sensitivity of NMR experiments. Sensitivity of NMR experiments is proportional to the gyromagnetic ratio of the excited nucleus multiplied by the gyromagnetic ratio raised to the power of 3 by 2 of the detected nucleus. The gyromagnetic ratio of carbon is 4 times less than that of hydrogen. You know that the gyromagnetic ratio of carbon is 4 times less than that of hydrogen. That is why carbon is much less sensitive. Thus, in Hetcor, the sensitivity is less in comparison to Cosy, because in Cosy, on F1 axis and F2 axis, we have PMR, but in Hetcor, though we have proton NMR on the F1 axis, on the F2 axis, we have C13. So for Cosy sensitivity, we will say 1 into 1, 3 by 2, 1, because Cosy the excited nucleus is proton, so 1 we have taken, and the detected nucleus is also proton, so another 1. So 1 into 1 raised to the power of 3 by 2 is equal to 1. But if we do a head core, then what happens? This remains as 1, but on the F2 axis now I have got carbon whose gyromagnetic ratio is 1/4 of proton. So I write 1/4 raised to the power of 3 by 2. It becomes 1/8. So the sensitivity of a head core experiment is 1/8. If both the nuclei are C13, that means on the F1 axis is C13 and on the F2 axis is also C13, it becomes 1/4 multiplied by 1/4 raised to the power of 3 by 2 is equal to 1 by 32. Thus, it is, you can see this particular experiment will be very, very insensitive and will take a long time to measure. Thus, maximum sensitivity can be obtained if both the excited and the detected nuclei are hydrogens. Sensitivity is proportional to root of time. Thus, if sensitivity is increased by a factor of z, we save time because as sensitivity increases, time will decrease. So, we save time by square of it. To get same sensitivity in C13 excited and detected case as when proton is used in Cosy, in both cases we need 32 into 30, that is approximately 1000 times more measurement time will be required if we take on F1 axis and F2 axis C13. Thus, starting with proton and detected proton is the best approach and is referred as inverse detection. Right here, what they do is that supposing we have to take polarization transfer from C13, what is done is we start with a proton, do one polarization transfer it to C13. From C13 again we transfer it to a proton. So on the F1 axis and F2 axis we measure proton, but there has been a polarization transfer in between. This is referred as inverse detection, and this is exactly what is done in HMQC and HSBC, more advanced methods. So do remember, sensitivity has no relation to natural abundance. And sometimes it is asked that why do you think that head core is takes much more time, or why do you think that a C13 2D NMR takes so much time? The students say that it takes more time because C13, the natural abundance of C13 is much less. But that is not the case. I have already explained it to you that the sensitivity is dependent on the gyromagnetic ratio and not on the natural abundance. A quick recap, a quick peek into what is HMQC or HSQC, though they are not in your syllabus, but then I'll just try and explain as to what they are. HMQC is heteronuclear multiple quantum coherence. HSQC is heteronuclear single quantum coherence. Both of them are much better than head core, though they give the same information as head core. That means both of them are giving us the carbon to hydrogen J1 coupling information. All the carbons which are directly attached to hydrogen by a J1 coupling, that is what we get in head core, and the same information we are getting from HMQC and HSQC. So the difference is, if you remember when we spoke about head core, I said that on F1 axis we have proton NMR and on the F2 axis we have C13 NMR. Here, whatever are the pulse sequences, that I am not discussing, but the net is that on the F2 axis you have a proton NMR and on the F1 axis you have C13, absolute opposite of head core. So HMQC and HSQC experiments are, however, detected on the proton atoms, contrary to the head core experiment where the detection is on C13. Proton detection is much more sensitive than C13 detection. We've already done that. That's if somehow we take proton in the, like, excited in this case is C13 and detection is on protons. So proton detection is much more sensitive as their gyromagnetic ratio is 4 times more of C13. So the HSQC and HMQC Experiments are used to determine proton-carbon single bond correlation, where the protons lie along the observed F2, that is the x-axis, and the carbons are along the F1, that is the y-axis. When I talk about carbon, I am talking about CNMR, and when I talk about protons, I am talking about PMR. So this is the information which you get from HSQC, HMQC and Hetcor, that is carbon hydrogen one bond coupling, 1J coupling. Then there is something with the name HMBC, heteronuclear multiple bond correlation experiments. It gives correlations between carbons and protons that are separated by 2, 3 and sometimes in conjugated systems 4 bonds. Direct one bond correlations are suppressed. For example, look here, this when I talk about HMBC, it will give me this linkage, that means the carbon here linked to this hydrogen. It will also give me carbon here linked to this hydrogen, but the direct one bond correlation which we get in Hetcor is suppressed in HMBC. Thank you. This is all for today. I hope you enjoy your day.